All right, if you've been following the evolution of decentralized systems, you already know scaling isn't just about faster transactions, right? It is absolutely crucial that we also scale trust. So in today's explainer, we're going to dive right in exactly how Ethereum is solving some pretty severe computational bottlenecks. We'll look at how it securely moves complex actions off-chain, starting with foundational cryptographic signatures like the ERC-191 standard's 0x19 byte prefix, and building all the way up to fully verifiable autonomous governance using TEEs and ZKML.
But first, let's set the stakes here. Why on earth do decentralized autonomous organizations, DAOs, still rely on such primitive one-token, one-vote systems when the blockchains they run on are, frankly, incredibly advanced? Well, it boils down to strict on-chain computational limits. We've got these massive global organizations, but they're kind of stuck in the past. They literally can't process nuanced social dynamics because doing that math directly on the blockchain is just way too expensive.
So, to fix this, we really have to bridge this massive gap between off-chain capacity and on-chain security. The solution? It's pretty elegant, actually. We just securely move the heavy lifting, the really complex computation, off-chain, while strictly verifying those results back on-chain.
Here is our roadmap for the explainer. We'll hit 1. The blockchain bottleneck. 2. ERC-191, securing off-chain data. 3. The DAO governance problem. 4. TEEs, hardware-based trust. 5. ZKML, cryptographic verification. And finally, 6. Verifiable off-chain governance.
Okay, let's jump straight into Section 1, the blockchain bottleneck.
Think of on-chain transactions as super expensive bank wires, complete with those painful gas fees we all know. They're secure, for sure, but severely limited in capacity. On the flip side, off-chain signatures are essentially like writing a letter. They're basically free, infinitely scalable, and you can process millions of them in seconds. But there is a catch. That free letter desperately needs a secure, tamper-proof seal so the blockchain actually knows it's authentic.
Which brings us right to Section 2, ERC-191, securing off-chain data.
Now, ERC-91 is just a truly elegant piece of engineering. Before this standard came along, if you signed a piece of data off-chain, there was a huge risk. Malicious actors could potentially grab that signed data, format it like a real Ethereum transaction, and literally drain your wallet in a replay attack. No way we could scale with that, right? Well, ERC-91 solved this by introducing the 0x19 prefix. This simple little 0x19 byte acts exactly like that wax seal we just talked about. It gets prepended to off-chain data, making it mathematically impossible for that signed message to be forged or confused for a real transaction.
So you might be wondering, how does that mathematical wax seal actually work in practice? Well, Ethereum transactions use a serialization format called RLP, or recursive length prefix. ERC-191 works by deliberately breaking that exact RLP encoding pattern. Because that 0x19 byte is followed by data in a way that completely violates standard RLP syntax rules, any node or smart contract looking at it will instantly recognize it as off-chain data, not a live on-chain transaction. It's an ingenious little trick, and it completely prevents those nasty signature replay attacks. And it's a remarkably flexible system, too. Take a look at how that 0x19 prefix pairs up with specific version bytes to give smart contracts the exact context on how to interpret that sealed data. For instance, version 0x00 locks the data down to a specific validator address, kind of like a multi-sig wallet. Version 0x01 actually paved the way for EIP712 structured data signing. And version 0x45, which corresponds to the letter E in ASCII, well, that's used for the personal_sign human-readable messages you probably click through every single day in your Web3 wallet.
All right, moving on to Section 3, the DAO governance problem. As this excerpt from the Arena paper on verifiable off-chain governance really highlights, DAOs desperately need to process rich, off-chain social graphs. Just imagine trying to calculate a PageRank-style trust score for, say, 10,000 DAO members based on their past contributions, peer reviews, and expertise attestations. I mean, doing all that math on-chain would literally bankrupt the treasury in gas fees. So these organizations are essentially forced to use primitive token-weighted voting simply because those strict on-chain computational limits restrict them from doing anything smarter.
Let's dive into Section 4, TEEs, or hardware-based trust.
So, one really powerful answer to computing these complex trust scores off-chain is TEEs, which stands for Trusted Execution Environments. These essentially act as tamper-proof hardware oracles. They use isolated enclaves right inside a processor to guarantee 3 absolute critical pillars. First up, integrity.
The hardware ensures the code running inside cannot be modified by anyone, not even the machine's actual owner. Second, confidentiality. The data remains completely encrypted in memory, which is an absolute game changer for private voting. And finally, attestation. The hardware actually generates a cryptographic proof that a specific algorithm was executed flawlessly.
Now, what if you don't want to rely on hardware? That brings us to Section 5, ZKML, cryptographic verification.
Right, so if you really don't want to rely on hardware manufacturers, we can use zero-knowledge machine learning, or ZKML. Instead of hardware isolation, ZKML generates cryptographic proofs that a specific complex governance algorithm, or hey, even an entire AI model, was run correctly on specific data. You get rock-solid mathematical proof of the execution, and you can use zero-knowledge circuits to maintain absolute privacy for things like voting choices or compliance checks. And the best part? It does all this without ever exposing the underlying inputs.
So looking at this, we really have two distinct trust models we can plug into our DAOs, totally depending on our security budget and privacy needs. Over on the left, we've got hardware trust using TEEs. This gives us great flexibility and speed, relying on that hardware isolation. Then on the right, we've got math trust using ZKML, which gives us absolute cryptographic certainty, even though, yeah, it can be a bit more computationally intense to actually generate those proofs. But the key takeaway here is that both models allow us to process incredibly complex logic safely off-chain.
Okay, let's tie it all together in Section 6, verifiable off-chain governance.
Here is exactly how we bring this whole shebang together to run million-dollar algorithms completely off-chain. Step 1. We collect thousands of off-chain attestations and signatures, all securely formatted using standards like that ERC-191 we talked about. Step 2. We feed that massive dataset into a verifiable service, using either a TEE or ZKML, which then calculates all those nuanced, multidimensional voting weights based on actual merit and expertise. And finally, Step 3. The smart contract back on-chain doesn't have to do any of the heavy math. It simply verifies the final cryptographic proof or hardware attestation. It's elegant, it's highly scalable, and it maintains perfect cryptoeconomic security.
Now, to wrap things up, with the recent introduction of standards like ERC-8004, which basically creates an ID card and trust framework for autonomous AI agents, the entire landscape is shifting dramatically. Think about it. We now have the infrastructure for off-chain verifiable governance, and we also have the infrastructure for trustless AI agents. So, I leave you to ponder this. What exactly happens to the future of decentralized organizations when autonomous machines, equipped with these verifiable mathematical proofs, begin actively participating in voting in our DAOs? It's a fascinating frontier, and the foundational standards we've explored today are exactly what makes it all possible.